In this video, we're going to focus on applications of functions and modeling functions to real-world situations. And one of the most important pieces of advice that I can provide is to just make sure you slow down and read the directions in the problem thoroughly. The advice I give my students is read the entire problem, do the problem, and then read the problem again to make sure you got all the key points of it. So let's read the problem through. Read each real-world situation and carefully define the input and output values using appropriate variables, then model it using a linear function with appropriate notation. Then find the inverse of the function defined. Example, an extra Uber driver charges one customer $58.50 for driving 10 miles, while another customer is charged $92.50 for driving 50 miles. Define an appropriate variable for the input and output and write a function to model the cost of an extra Uber ride per mile and use it to determine how much a 30-mile ride would cost. Start simple. The first thing it says is define an input and output value. And that is really important because if you do that backwards, the whole problem will be frustrating. And in fact, even if you do it backwards on an SAT or a standardized test, they probably will work it through in that direction and you'll think you have it right, and in fact, it's actually in reverse. So how do you determine the input and output? Some teachers will call, and some textbooks will call input the independent variable and the output the dependent variable. And that's a good way to think about it as well. So it just depends on your text or your standardized test that you're taking. So the way you determine the input or independent variable is you think about which of these two items is producing the other. Is $58.50 producing 10 miles, or is 10 miles producing a cost of $58.50? And when you say it like that, it's pretty obvious that the 10-mile ride is producing that cost. I mean, this is our input here, and it's producing this output here. And same thing for the second one down here. And we'll talk about why there's a second one in just a minute. So the input is the miles. I'm inputting a mile to the driver, and the driver is outputting a cost to me. And so, hey, we did the first step. The second step is to write a function model. So it doesn't make sense to use f of x in this case because there is nothing that's relating f or x in the problem. So we want to change that to c for cost per mile. Notice that the input is inside the parentheses. Very easy to remember that. Input inside the parentheses. So now we're going to try to think, okay, well, what kind of function is it? And this is a perfect example of what happens on an SAT or a standardized test, or later if you were to take an AP test. The actual function type is up here in the directions. And I did underline it so that you could see it. A lot of times that wouldn't be underlined. So knowing that it's a linear function, we can go back to Algebra 1 and talk about y equals mx plus b. And while we're at it, we can talk about whether or not they provided us with a slope or a y-intercept. So if you have a slope, you'll have a very similar situation, but it would be what's known as a unit value, meaning something per one of something. So if I said that the Uber driver is charging $1.25 per mile, per 1 mile, that would be my slope. I don't have that. I have a ratio of different things happening. Also, if they told me where the initial cost was, if it said the extra Uber driver is going to charge you $25 to start the ride or to begin the ride, that would be my B, or my initial value. I have neither of those, so I've got to start by finding the slope. And you can recall from Algebra 1 that the slope is m equals y2 minus y1 over x2 minus x1. In upper level classes like Algebra 2 or beyond, especially in science, that model gets changed to f of b minus f of a, meaning the output of the second value minus the output of the first value, f of b minus f of a, and then over b minus a. So let's see if we can figure that out up here. My first input would be called a, and it is producing f of a. And then my second value that they gave me down here is b, my second value, and it's producing f of b. So that's a pretty easy substitution at this point. What we're going to do is we're going to put in here f of b, which is $92.50, and we're going to subtract $58.50, and then we're going to divide that by b, which was 50 miles, and subtract 10. Now, one way to really remember this is to think, okay, $92 here was produced, right? $92 was produced by 50 miles, and $58 was produced by 10 miles. So I always like to tell my students, your output should have the input directly below it in each case, and you won't make a mistake. So that's obviously a calculator item. So the TIs have a nice feature where you can put it into fraction mode. Casios, the newer Casios, have a similar method, and you can always use Desmos if you do not have a calculator. That would also work just as well and even looks like this. So I'm just going to type it all in there at one time, and once I do that, I find out that the rate is 85 cents per mile. Sometimes that's all that's asked, is what is the rate? Right? And so you would say, well, that's 85 cents per mile. And that's sometimes, especially on an SAT, all that's asked. Okay, but in this case, they're asking for the whole function. So we're going to actually input that into y equals mx plus b. So y is equal to 0.85 x plus b. Now, if we want to switch that over to our better notation, right, that would be what it would look like in Algebra 1. I could just go ahead and say c, because that's our y in this case, is equal to 0.85 m plus b, if I prefer, okay? Or you could just put it all together at the end. So what we're going to do now is we're going to use one of the inputs and outputs. So I prefer to just use the first one because it's smaller. And we're going to input the fact that driving 10 miles costs $58.50. And again, I just got that straight from the problem. And it's kind of interesting when you start seeing these things happen and you understand where these things in Algebra 1, why they mattered. So $10 made $58.50, but now I have the rate. So now I know that that is being charged at 85 cents per mile. Maybe that's why it makes a good sense to go ahead and just switch out of this mode and go here. I think it'll make the problem make a little more sense. And so then we just multiply that through, giving us $8.50, or just 8.5 because we're just doing math in this case. And then over here, this drops down because there was no math to do there. And then I'll subtract $8.50 on both sides, and then I'll have the initial cost. Okay, so sometimes, just to be tricky, in SAT might ask, what's the initial cost? And that way, what they're testing is, do you know the equations you learned? But then at the same time, do you know what the pieces of those equations mean? So in this case, the initial cost, or B, the beginning, if you would like to call it that, is $50. So let's put it all together, because our problem asked us to make a function. So our function would be C of m is equal to 0.85 m plus 50. And what that's saying in the real world is that the cost per mile is 85 cents per mile plus the initial cost of $50 just to call the extra Uber driver. Okay, so step A is done. Step B is asking me now to find an inverse of this function. So starting with this function from part A, the question is, how do I find the inverse? And once I find the inverse, it would like me to plug $118 into the inverse. Now, some students may say, do I even need the inverse to be able to do the 118 part? You really don't. I mean, you could put 118 into this for the cost and then solve for m. But in this problem, I'm just trying to show you why inverses are useful and why producing an inverse would actually do something that would help us. So we're going to do this part second. So first, let's find an inverse. And remember, the way an inverse works is you switch the input and output. It probably would help if we kind of go back to the y equals mx plus b model, just so we stay consistent with what you probably learned in class about inverses. So what you do is you switch x and y. So you're going to switch this to x and this to y. And then once we get through that, we'll go back and use the correct function notation for this problem. It'll probably just be more consistent to do it this way. Okay, so pretty easy to solve this. We're going to subtract 50 on both sides. So now I have x minus 50 is equal to 0.85y. And then I'm going to divide each piece of this by 0.85. Once I do that, it's important to understand that it's not a good idea to just draw a big line and do that. You would actually want to do each of these with 0.85, or else you would not know the rate or initial value for the inverse. And please keep in mind there's actually a little 1 right there. Man, that's important for upper level math classes. It seems subtle, and it is, and knowing that will really help you. All right, so let's reduce both of these. So 1 divided by 0.85 is 1.176, and then negative 50 divided by 0.85 is negative 58.823. So this became 1.176, and this value here was minus 58.824 actually, so minus 58.824, and that equals y. But to reverse the actual notation here, or to find the actual inverse, all you do is you switch these, right? So inverse means to switch, so we're going to switch these two things. So this will become c of m for the y here, and that's going to equal 1.176. Now, be very careful. This was an m, right? So now this would be a c, or the cost, minus 58.824. Okay, makes sense. The c of m became, oops, I said and didn't write it down. Give me 1 second here. That would become m of c. Sorry if that was, sorry about that little typo there, or just wrote it down wrong. So m of c would switch, as I said. So m of c meaning mile per cost instead of cost per mile, and then the m changes to a c. So now we can easily do the problem, find the inverse, and use it to find the miles you could ride with $118. So the miles I could ride with the cost of $118 would be 1.176 times $118, and then minus 58.824. And then I just type that in my calculator. So let's see here, 1.176, and then 118, and then minus 58.824, hit enter. Syntax error. Don't ever hit quit here. Always hit go to so you can see what your typo is, and I accidentally put an extra parentheses in. So I just delete that, and then we got it, 79.944. So the miles that can be driven with $118, that's why that function notation is so important, so you can see what that means, would be equal to 79.944 miles. And the reason I'm putting units on this question is because it actually asks on the question how many miles, so you'd want to include units, where I didn't include units over here because I'm writing out an equation, which equations do not have units. In this example, we're going to be focusing on applications of composite functions. Composite function just being one function that's been substituted into another. So directions. Read each real-world situation and carefully examine each defined variable and function. Area and volume. A spherical weather balloon is being inflated in such a way that the radius is given by r of t is equal to 2t minus 1. Assume that r is in meters and t is in seconds, with t equals 0 corresponding to the time that the inflation begins, meaning that's the initial value. The surface area is given by A of r is equal to 4 pi r squared, and the volume is given by V of r is equal to 4/3 pi r cubed. Compute and simplify A of r of t and V of r of t. So that just means it wants you to take this function here, this radius function, and it wants you to substitute it into the r for the area function. So let's take a look at what the math would look like for that. So A of r of t, right? A of r of t. You would just use the same formula that you see there for area. You have a 4 and you have a pi, and then instead of the r, you would use a parentheses because we are substituting. That's all composite means. Just don't forget that there is a square on the r, so you'd want to put a square on the parentheses. And then inside the parentheses, you're going to take this and put this in for r, so that would mean you would have a 2t minus 1 in here. So this is r. It is, as you can see, 2t minus 1. That r matches there. And now we're going to simplify that algebraically. So we're going to use Gelndas, or the order of operations. And first thing we're going to do is look at the g, the grouping symbol. There is nothing to combine. So we're going to move to the exponent, the square, and that means to write this down twice. You cannot distribute exponents into expressions with addition and subtraction. So we have to write it down twice. That's what square means. It means there are two of them multiplied together. And then what we're going to do there is we're going to have to either FOIL this or use the area model. I have really started to like the area model or the box method over the last couple of years. So you write out the first one in a row, and the second thing you're multiplying you write in a column, and then you draw an area model or a box model around those items, and then you can find the answers and place them into the corresponding boxes. So 2 times 2 would be 4, and then we have t times t, which is t squared. And then 2t times negative 1 is negative 2t. And then 2t times negative 1 is negative 2t. And then negative 1 times negative 1 is positive 1. Beautiful thing about the box or area method is that the like terms are always right here on the diagonal. So the items that we have not used are the 4 pi. We're just going to drop those down. So the area model, A of r of t, is going to be equal to 4 pi, and then we're going to add our like terms up. So we'll have, in a parentheses, 4t squared. These two are like terms, so they add up to negative 4t, and then plus 1. And then the last thing we're going to do is we're going to distribute the 4 pi in, because remember, we're going through Gelndas, did the grouping, did the exponents, now we're going to do the multiplication. So if I multiply this times this, I would get 16 pi t squared. If I multiplied 4 pi times negative 4t, I would have negative 16 pi t. And then if I multiply 4 pi times 1, I would get 4 pi. So that would be what it would look like simplified. Some people might want the factored out version, but these are both equivalent. So there is the area model. To do the volume model, V of R of t, be very similar, but we'd be using the volume model that was provided. And those volume models are just from geometry. This area and volume model, they're just from regular old geometry. Would be 4/3, and then pi, and then a parentheses, and then a cube. And then inside of there, we're putting r, the same r we had here, so that would be 2t minus 1. And then that would mean we'd have to write it out 3 times. So we would have to actually write this out, 2t minus 1 times 2t minus 1 times another 2t minus 1. But conveniently for us, we already know what 2 of them are. Like, we already know what this is, because that is right here. So we already know that. That would be 4t squared plus 4t, I'm sorry, minus 4t. Let me fix that. So 4t squared minus 4t, and then plus 1. Again, the same thing we had right here. And then I'm just going to box that up, because that is what that equals. I'm just going to put this one down the column, 2t minus 1, and then we'll just go ahead and do the area or box method on that. So it actually goes through pretty quickly if you already know what the square is. And some people memorize a way to square things. You feel free to do that if you want to, but it doesn't hurt to just do that. So 4 times 2 is 8, and then t times t squared is t to the third power. You can see now that it's cubed. 4t squared minus 1, times negative 1 is negative 4t squared. And here we have 2 times negative 4, which is negative 8. And then t times t is t squared. Notice that diagonal has the same variable. Negative 4t times negative 1 is positive 4t. And then we have 1 times 2t again. Notice again that we have the same variable on the diagonal. And then 1 times negative 1 is negative 1. So this volume will be 4/3 times all of that together. So let me give myself a little bit more space here. All right, so V of R of t will be, drop down the 4/3 pi, we never use that, so 4/3 pi, and then times everything in that area model with combined like terms. So 8t cubed, negative 4 and negative 8 are negative 12t squared. 4 and 2 are 6t. And then we have minus 1. And again, if you want to, you can distribute this through. So that would be 4 times 8 divided by 3, which would be 6 pi t cubed. And then 4/3 times 12 would be negative 16t squared. And then 4/3 times 6 would be 8t. And then, sorry, these should have pi's on them. Don't forget it's 4/3 pi. So 16 pi t and 8 pi t. And then 4/3 times negative 1 is negative 4/3 pi. If you wonder how I did that so quickly in my head, what I did here was I did 4 times 8, which is 32, divided by 3. So that actually doesn't work out. I actually made a little boo-boo there, so let me fix it. So that would be 32/3. My brain played a little trick on me there. So let's take a look at, so that would be 4 times 8 is 32/3. That does not reduce, so my brain played a little trick on me there. Let's go through the rest of them. 4/3 times 12 would be 48 divided by 3, so that is 16. And 4 times 6 is 24 divided by 3, so that would be 8 pi, and then 4/3. Sorry about that little mistake there. Okay, so that would be V of R of t. Okay, so now what we're going to do is we are going to use this. That did take quite a while, but these two answers, right? This answer for A of R of t and V of R of t, they're going to be used to work on the rest of the problem. So it now wants me to find A of 2 and V of 3 written in terms of pi. So A of 2, it just wants me to put 2 in this equation. I could have put 2 into here, found the answer, and then plugged it into here. So it's interesting. You can do it both ways. It would actually give you the same value. So that's an interesting thing to think about. So if I were to find A of 2, A would have to go into, notice it doesn't go into T, it has to go into R. So it probably would be easier to find R of 2. Okay, so R of 2 would simply be 2 times 2 minus 1. So R of 2 is just 4 minus 1, or 3, and then plug that into here. So A of 2, remember this is kind of, you're doing word problems, so you have to pay very close attention. The 2, right, has to go into here and then that would then go into there. So that would be 4 pi and then times 2 squared. Okay, so that would come out to 4 pi times 4, or 16 pi. Notice it wants it in terms of pi. So you could also have taken the 2 and put it into here as well. And you would have gotten the same answer, but obviously it would have been more complicated in there. Okay, so to find the other one, I'll do that in a different color. To find v of 3, same idea. I'm going to put the 3, it could go into this, okay? Or I could put the 3 into here and then put that into there. So that would be 2 times 3 minus 1. So v of 3 would be 6 minus 1, or 5. And to plug that into my volume equation, v of 5 would be 4/3 pi, and then 5 to the 3rd power. And 5 to the 3rd power is 125. So let's take a look here. Maybe we need to use a calculator for that one. So 4/3 times 5 to the 3rd power is this number, but a lot of calculators have a feature where you can turn it into a fraction, and on the TI you hit math, hit 1 to convert to fraction, enter again, so you just get 500/3. Maybe we could have done that in our head, but I wanted to show you that fraction feature. On Desmos it's a simple conversion, and on Casio is similar to that. Okay, so remember it wanted this in terms of pi. So the question is, which one is smaller? And part of that, right, it's an interesting comparison because this one is much bigger than this one, but it also has to do with units. Remember, this would be units squared, okay? So this one would be whatever the units are. In this case, the units are meters. So this one would be meters squared. And this one over here would be meters cubed, so cubic meters. So they're actually not particularly comparable. This number does seem larger than this number, but remember, the comparison, because of the units, is they're really not a comparable unit of measurement. Okay, it's like trying to compare a piece of paper to a box, basically. Like this is a, just a piece of square unit, and this is a cubed unit. So it's again, it's like trying to compare the piece of paper you're writing on to a box that comes in the mail that doesn't have a comparison. So now it says use A of R of t to find the time at which the area of the balloon is 36 pi. And this is such a great question because we have these two answers, right? We had the first answer and then we distributed that answer. So now the question is, right? The question is, which of these would be easier to set equal to 36 pi? And the answer is this one is. Why? It's already factored. So a lot of students will talk about factoring and they'll have some trouble with when they need to use factoring. And factoring is something that is only used when you are dividing. So we're not dividing in this problem, or when you are solving. So it's really important to understand how factoring works. The purpose of factoring is to break something down into smaller pieces, which the only reason you would want to do that is to reduce a fraction for division, or to divide using a polynomial, or to solve. So again, I had these two to pick from. I picked from this one because of the fact that it's already factored with a GCF. So to solve this, all I would do is just divide this GCF on the other side. Notice the like terms, which makes that convenient. And so the pi's actually cancel out, which you would want that to happen or else you would have a mess. And so 36 divided by 4 is of course 9, and then I'm left with this function. And the question is, well, what do I do to solve this? And this is going to involve factoring skills from Algebra 1 when you did quadratics. So all quadratics have to be set equal to 0. And once you set the problem equal to 0, you do that by subtracting what was there originally. So get rid of 9 by subtracting it, okay, which will give you -8 as a result. and then ask yourself first if there's a GCF before you start factoring this. A lot of students will be like, I can't factor that because the leading coefficient is too large. And we will be, in Algebra 2, we obviously will be doing problems with lead coefficients, but in this case, they all have a 4 in common, so I can easily factor that out, and the problem becomes very simple, right? Got one step ahead of myself there. It becomes very easy because you factor the 4 out by dividing this by 4 and this by 4 and this by 4, and you end up with that quadratic, which is very easy to factor, because with a minus, you always have a plus minus. So if you don't know that rule about factoring, if this is negative, it's always a positive and a negative, always, no matter what you're doing with quadratics. And then I just need to think of factors of 2, which is only 1 times 2, that will then subtract to negative 1. So you'd want to put a 1 here and a 2 there, because 1 minus 2 is negative 1. And then to solve it, remember we're trying to solve this, you would set these two pieces equal to 0. And again, that's just from Algebra 1. So one answer doesn't make sense because you get time equals negative 1. And the other one, if I set this one equal to 0, I get that at 2 seconds, I'm going to put a unit on it, so at 2 seconds, the area of the balloon is 36 pi using this model. Now keep in mind, that model also uses the fact that the radius is this. So it's kind of an interesting, that shows you what the composite nature is. It's a compounding thing. So that's interesting how it actually solved two problems at once. Okay, so now use this time from part C to find the volume at the same moment. So now it wants me to take this amount, and that was where the area was, and it wants me to take the area's time here and put it into the volume equation. So again, we could put it into this huge mess, or we could put that back into this that generates the radius, and the radius will generate the volume. Remember, the time generates the radius, and then the radius will generate the volume. So it's kind of like doing part B. So if we find that volume at 2, the equation for the r to find the radius was 2t, so it'll be 2 times 2 and then minus 1. So, oops, that's an r. It's kind of hard to read that. That's let me fix my handwriting there. Okay, so the r equation, right, at the time t, right? So that would be r of 2 would be, the radius at 2 seconds would be 4 minus 1 or 3. And now we're going to plug that into the volume equation. So the volume at 3 radius is 4/3 pi 3 cubed. 3 cubed is 27. And 27 divided by 3 is 9. 9 times 3 is 36. Again, let's double check that on the calculator, and then I think I understand why this other question is being asked. So 4/3, leave the pi out, 3 cubed, and that gives us 36. Just making sure. So keep in mind, this one right here would be meters squared, and this one is meters cubed. So the question is, what does this mean? How could this possibly be the same value as this? They're not. This is like a square sheet of paper, and this is like a box. So even though we have the exact same answer, they're not talking about the same thing, which I think is pretty interesting. So in this application problem, we're going to take a look at how real-life problems apply to absolute value equations and inequalities. So read each real-world situation and carefully examine each defined variable and function. Example: an absolute value function can be used to show how much a value deviates from the norm. The average internal body temperature of humans is 98.6 degrees Fahrenheit. As a function, the equation is V of t equals the absolute value of t minus 98.6, where V of t is the variation in temperature from the norm and t is the temperature of the patient. Part A. the temperature can vary by as much as 0.5 degrees and still be considered normal human temperature variation. Write an absolute value equation to model normal human temperature variation and solve this equation and graph the solution set below. So this is a great example of an SAT or standardized test question in which they actually give you the equation and they just ask you to solve. So sometimes there's work to do, but in this case, all you have to do is take this number and put it in for variation. So it's just going to end up looking like this, and then you just have to know how to solve it using an absolute value model. So that's not so bad, other than the fact that it's a word problem and you have decimals. Okay, so how do we solve absolute value? Remember, absolute value is defined as the distance from 0. So what it's saying is that 0.5 is equivalent distance from 0 as negative 0.5. So I have to solve both of those equations because the absolute value is basically saying that those are the same equivalent distance from 0. So in this case, they would be the same value. All right, so we take 0.5 and we set it equal to t minus 98.6, removing the absolute value symbol, because now we're going to set up a second equation in which negative 0.5 would also equal t minus 98.6. And then we just solve this equation, and it's actually just, both these equations are just one-step equations. I'm going to add 98.6 to both sides. So I add it here and it cancels, and I add 98.6 here. And that will give me the upper variation of human acceptable temperature, and that would be, add these two together and you get 99.1. So 99.1 is still considered a normal temperature. And if you've ever exercised or woken up from a bad dream where you've gotten really hot potentially, you might have a temperature of 98.1, and it's not considered ill, it's just considered a variation within your temperature. And some people will actually run a higher temperature normally as well. So same thing on the lower end here, but in this case I would get 98.1, and that is equal to the lower end of temperature. So if I were to graph this on a graph, on a number line, it probably would make sense to maybe use a unit of just one, or maybe we'll go by 0.5s. So this would be 99 degrees, this would be 99.5, and then 100, and then here we would have 98.5, and then below that we'd have 98 degrees. And so if I were to graph this pretty easily, I'd put 98.1 right here as a dot, and 99.1 right here as a dot, and it would just look like that. That would be the two upper and lower ranges. To color it in and go beyond it, that's the actually second part of the equation. So these would be the range of temperatures, but to make it look more, to make it a little bit, by the way, if you want to put a unit, you just put a degrees Fahrenheit on there. That's the second part of the problem. So if I look at the next part of the problem, hypothermia, dangerously low, or hyperthermia, indicating a fever, occurs when the body temperature is outside of the range mentioned in Part A. Write an absolute value inequality to model temperatures in this range and solve this inequality and graph the solution set below and use set notation to denote the answer. So what they're talking about, let's do the visual first. If I take a look at this visual that I have over here, 98, 98.5, 99.5, right, so 98, 98.5, and then 99. If I take 99.1, and I'm going to use an open circle because remember 99.1 is considered acceptable. If I go this way, I have hyperthermia, hyper meaning above. And if I have 98.1 here, again, open circle because at 98.1 I'm still considered okay. And I go this way, that would be hypothermia. So if I think about this in terms of an inequality answer, that would be if my temperature is below 98.1 degrees, or if my temperature is greater than, right, greater than 99.1 degrees, I would have these two medical situations. Both are dangerous. So that's the answer. The question is, well, what is the inequality? All I would have to do is take 0.5 and make it, right, and I have to put an inequality here. And so the question is, what inequality do we use to denote this outside of range? And it's a little confusing because typically to do inequalities, what we're going to do is we would want that number to be over here, and it would make a little more sense. So I'm actually going to place it over here, and I'll show you why that's important. So the question is, well, what would it be? So if we were to look at the two solving methods, right? Remember, we're going to do the same thing. We're still going to have the exact same situation that we had over here. T minus 9, sorry, it should be 98.6. Let me fix that. All right, so what's going to happen is we're going to have T minus 98.6. And remember, we want to make sure that when we add this and get 99.1, that it is greater than this. So I guess the question is if we start off that way, will that in fact give us the right inequality? So let's just start off by saying greater than, because we know that from the graph, 0.5. Okay, so if we add that to the other side, we would have greater than 99.1. So yeah, that looks like it works. So the question is, knowing how absolute values work, if we make this a greater than symbol, what's going to happen in the world of absolute value is that would have to reverse, right? That would have to reverse around and become negative. That's what we learned about absolute value earlier in the unit. So if I add that to the other side, I would have T is less than, add 98.6 and negative 0.5, I'd have 98.1. It's kind of interesting. I kind of worked this problem backwards from the graph, but this is the equation right here. This is the equation that would produce the graph that we could already sort of visually see from this side. Notice I did not use an equal sign because of the fact that I don't have these values, if they're inclusive, are over here, meaning that you're healthy. All right, there's one last part to this. It says, at home you discover your old thermometer is missing temperature, is measuring temperature incorrectly by 2 degrees, and this will alter the model to be V of T is equal to T minus 98.6 minus 2. If a person is told that their variation in temperature is 1.1 degrees, use the equation to find their actual body temperature. Okay, so what that's saying is it just wants me to put this value in for the variation. So 1.1 is equal to the absolute value of T minus 98.6 minus 2, and then I'm going to solve this equation. Now this is an important thing to understand because these absolute value bars, you can't just add the 2 to both sides and get going. You can't just make this plus or minus. There's a certain way that has to be done. You have to solve for the absolute value symbol. So you have to actually add the 2 to the other side before you begin the solving process for the absolute value. So this now becomes 1.3 is equal to the absolute value of T minus 98.6. And now I can actually solve it. That feels very awkward in a real life problem, but when you study how to solve absolute value, you have to solve for the absolute value symbols before you apply the fact that you have a positive and a negative one. It's a really critical step that's forgotten by a lot of students. So make sure that you solve for those absolute value symbols first. Okay, so there's my first equation, and my next one is negative 1.3 is equal to T minus 98.6. And then I just solve both of these. So if I add 98.6 over here to both sides, pretty easy to do because everything lines up. So you get a 0.9 here, and then here you get a 9, and then here you get 99.9 as your upper range for your temperature. Then if I add 98.6 over here, now this one's a little bit confusing because of the fact that it's a negative one, so we're definitely going to break out the calculator. So negative 1.3, again, you could use Desmos or use a Casio or whatever you prefer. So this lower range of temperature is 97.3. So that would be the lower range, and this would be the upper range. So to answer the question, use equations to find out the actual body temperature. The body temperature, where you can't figure out the actual body temperature, you can only figure out that it is between these two things. So if you were to use interval notation on that, you would use, you would say it's between 97.3 and 99.9. And we could probably go ahead, since we have an equal sign, and use a bracket for that. And that reminds me, up here, I use this notation, and the answer asked me to put it in set notation. So this one would be anything below 98.1. That's a weird thing to put in set notation because human body temperature, obviously, you would at some point not be alive. So I think I'm just going to keep it in this notation. In this problem, we're going to take a look at the rate of change and how to make a larger chart based on more values of the rate of change. And then we're also going to graph the original data and the rate of change and do an analysis of the graph using terms like minimums, maximums, increasing and decreasing. So one thing that I'll mention in this is that you probably are going to want to take some time and pause the video and complete what's going on your own paper as I go. All right, so let's take a look at what the problem is asking. The following data is a data set corresponding to the times achieved every 10 meters by Carl Lewis on the 100-meter final of the World Championship in Rome in 1987. So these values are given to you, and you're going to graph them here. And then for each successive time interval, calculate the average rate of change of the distance, and then what is a common name for the average rate of change of the distance? Well, the common name for the average rate of change of distance is velocity. Okay, and velocity is a measurement of the input and output of position. And the way that units work for all rate of change, not just this problem, is it's the output per the input. So the output is meters. Use this line for per, and then the input is seconds. So remember, output per input, so meters per second. So what you're going to do is, to figure this out, you're going to use the rate of change equation, right? The rate of change equation is f of b minus f of a over b minus a. And you're going to do that in here. Maybe you can do this box, or you can use scratch paper. And so remember, this would be f of b, this would be f of a. So it would be 10 minus 0, f of b minus f of a, over the time that this was made by, or 1.94, the input of 10 minus 0, and then you're going to use a calculator and figure out what all those values are all the way across like that. The next one would be 20 minus 10 over 2.96 minus 1.94. So I went ahead and pre-did a lot of this problem, as you can see here. And so what I'm going to do is I'm going to ask you to figure out this chart. Let me zoom in on it. Exactly like I said, you're going to take 10 minus 0 and 1.94 minus 0 and simplify that on a calculator, and then 20 minus 10, and then 2.96 minus 1.94, and then simplify that on a calculator. All the numerators are 10, if that will help you. And then you're going to, from there, you're going to take the time and make a graph. So again, I would pause the video and graph the position here. Position is going from 0 to 100. There are 10 dashes, so I went by tens. And the time on the horizontal axis, he ran the race in 9.93 seconds, so I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did the same thing for the velocity of 1, 2. The time is always the same. So go ahead and make that graph. Once you do that, you're going to want to pause and make this graph. Notice the time again is the same, but the velocity I only went up to 12 because his largest velocity is 11.65. So I just went by 2's, and then I took these values here and I graphed them as the output. But the input I just did by averaging these two numbers. You can eyeball it between 0 and 1.94, just kind of in the middle, or you can literally add these together and divide by 2. So go ahead and do that now too. So once you've made both graphs, the analysis of graph problems are fairly easy, and it's really interesting why this chart is so important for some of the preceding questions. So identify the increasing and decreasing consecutive intervals for position. Well, if you look at this graph for position, he is always increasing his position. And remember, he's running a race, so from 0 to 9.93, he is increasing his position. And you might wonder, well, why do we have a parentheses and then a bracket? Well, at the beginning of the race, before the gun goes off, the starter gun to go off, he is not increasing, so I do not have a bracket there. But at the end of the race, he is still moving forward, so I bracketed it. Okay, so where is he decreasing? None or does not exist. The AP and standardized testing do allow D and E for does not exist. You can't say nowhere or nothing. So none or does not exist. He's never decreasing his position. So identify the relative and absolute minimums for his position. Again, we're still talking about this graph. So his smallest position was at the very beginning, he was at 0 meters, and at the very end, he was at 100. So as a point, that point is 0, 0 as the relative minimum. It's the only minimum on the graph, and his absolute minimum is also that value. His absolute maximum was 9.93 in 100 meters. He ran a 100-meter dash, so that's his relative and absolute maximum. Again, this is a lot easier if you've made the graphs and done the chart, so you want to make sure that you pause and go back and do that if you have not done it yet. So when was, the next question, when was the velocity positive? So looking at the graph, you can see his graph is always positive because it's above the horizontal axis right here. As long as it's above this value, it's positive. So the velocity is always positive. Now, why is that so important? You'll see in a minute, because he clearly, if you look at this graph, he's not always doing the same thing, and that's another concept we'll talk about in the next problem. But in terms of his velocity, his velocity is positive from 0 to 9.93. And another way of thinking about that is he's always moving forward. Velocity has direction. So if your velocity is positive, it means you're simply moving forward. So when is his velocity negative? His velocity is negative, none or does not exist, because that would mean that he turned around in the race and was going backwards, and that does not happen. So now here's where we get to these curvy aspects of the graph. When were the velocities rate increasing or decreasing? Okay, this is known as acceleration or deceleration. And what time interval was he decelerating or accelerating on? So when you look at the graph, it's a little hard to tell, but if you go back and look at the actual numbers, you can clearly see that starting from here, his rate is going up, right? So 5 and then 9, wow, he sped up there. He did it here. He did it here, meaning this value is bigger than this one. This one's bigger than this one. And again, he still did it here, but then all of a sudden here, he's kind of flat. Notice he's just sort of cruising right here. These are flat. He's not really going up. And then he goes up a little bit more right here. Boom, between here and here, he's going up again. And then here, he actually decelerates right there. And you can see that in the graph. That little is right there. And you can even see in the graph right here that he has now gone up. And you can even see the flatness in these values here. So that's why this rate of change chart is so important to look at with this graph. So you can see that his acceleration is, his velocity is going up here, creating acceleration, then he's flat, and then he goes up a little more. So from here to here, I'm just going to use the times above, right? So from 0 until this last value here, from 0 until 5.64, he was increasing his velocity or accelerating. He also does it a little bit right here. So those values, if you go back up and look at the chart, are between 8.22 and 9.07. And then at the very end, he's decreasing. So from here to here, he's decreasing. Okay, and so what it would be called in the middle is constant velocity. So the next thing is, during a sprint, why should his acceleration never be negative? Well, you are told as a sprinter to just run as fast as you can the whole time in order to have your race have a constant acceleration. You want your acceleration the entire time to be positive. Okay, where did Carl Lewis attain his maximum velocity? So I can look at that in the velocity. It looks like his maximum velocity occurred right here. So you could say between 8.22 and 9.07. So where did he attain his maximum velocity between 8.22 and 9.07? Some runners are running their fastest as they cross the finish line. Does this appear to be true in this case? No, he's actually slowing down. This could have happened because he knew he had won, or his muscles could have just given out. So sometimes, you're told to be running as fast as you can as you pass the finish line, but sometimes, you might just get a little bit confident, or maybe your muscles have given out. So does this running style make sense for a long distance runner? Why or why not? The answer is no, not really, because a long distance runner needs to start out fast to kind of get position amongst all the runners, because there's not only 6, there could be 600 people in the race. And then you keep a consistent velocity, and then you speed up at the end. So it's not a run as fast as you can the whole time. It's more of a run as fast as you can, kind of keep consistent, and then at the end, and that sometimes is called a kick. All right, I hope you've enjoyed these videos about applications of functions, and thank you for watching.